This is the second video of the 9.2 19.1 series. It is the HL version of the voltaic cells, and it explains where that voltage number that we got when creating our voltaic cells, where that number actually came from. These are called standard electrode potentials. There are going to be a series of units and terms you need to use. You can either write these down or you can have access to them in your textbook so that you can refer back to them. It's up to you how you decide to go about that, but it's on page 432. First is the term amp. The symbol for amp is A. It is the SI unit for electric current. Its unit is I, and that's how we represent it. Coulomb, it's the way in which we represent Coulomb is C. The SI unit, this is the SI unit for the electric charge, so how much charge is moving through, and it is represented by Q. And so Coulomb is the amount of charge transported in 1 second by 1 amp. So based off of that, there is an equation which we can use, and it is Q equals I, so amp, times time. Or you can say C equals A times S. And these are the units version. Both mean the same exact thing. Now, as we go through and it's looking at the amount of charge transported in 1 second by 1 amp of electric current, what's moving that electric charge is the electron moving through the voltaic cell, that external. And so we know that 1 electron has a coulomb of 1.602 times 10 to the negative 19 coulombs. And so 1 electron doesn't actually produce very much voltage and nothing really worth speaking about. And just like in everything in chemistry, it's all about the mole. So 1 mole of electrons, what does that equal? Well, this is significant. This is 96,485.34 coulombs per mole. Now we're talking. That is a lot of movement of energy. This is known as Faraday's constant. So I guess you can predict who made this constant, and it will be represented as a capital F. And so this is the number we'll use. We'll use Faraday's constant whenever we're looking at how much are the electrons actually supplying in their energy. A volt, also known as V, is the SI unit for the potential difference between 2 points, between the 2 half cells, so between an anode and a cathode. All right, so we know volts equals joules, so energy, times coulomb. So it is literally the amount of energy per coulomb. And then we have the electromotive force, also known as your EMF. And this is the greatest potential difference a cell can make based on its voltage, also known as a cell potential. And so this is in the standard conditions. Ideally, how much potential could a zinc half cell make with a copper half cell? And that was what that plus 1.10 volts is. Now, would we probably ever really see that? Probably not, because we're not necessarily running under standard conditions. So these are all the different units in which we will see and use, and hopefully by the end of this video, which will be a longer video, I apologize, you'll start to understand where everything comes in. So an EMF, or the electromotive force, is created as the electron flows from the negative half cell, your anode, to the positive half cell, your cathode. All right? So the difference between those 2 half cells is the magnitude of your voltage. This is also known as your E cell, which is what we're going to learn how to calculate, or also what's called your electrode potential. Now, how do we know what this difference is? Well, it's based off the relative reducing power, so the reactivity series, and the placement of the metals and or nonmetals on that series. And for this, we need a reference point. We need to know essentially what is the 0 point, who's neutral, so we can figure out what the difference could be. And that 0 point for us is arbitrary, but it was hydrogen. It's called the standard hydrogen electrode, also known as SHE. S-H-E. And so it is a completely arbitrary point, but essentially they've taken all the half cells, hooked them up to hydrogen, and they have therefore created a reactivity series all based off and compared to hydrogen, creating a standardized system. So what that standardized hydrogen electrode looks like, and here's the setup. All right, so you have hydrogen gas, as you can see and probably determine because it's a standard hydrogen electrode. So hydrogen gas is going to be pumped into, because it's a gas, into the cylinder at 298 Kelvin. And because it is a gas, it has therefore a pressure applied at 100 kilopascals. Then that gas is going to be produced. Now in this column, this tube, we have our electrode. Our electrode is a platinum electrode. The reason we have platinum is because it is an inert metal and it will not partake in any oxidation reduction reactions that may take place. And we have to use platinum because hydrogen doesn't have its own pure metal. Okay. It will also act as a catalyst for hydrogen reduction because it's coated in a finely divided platinum, which increases the surface area for increased absorption of hydrogen gas. So as you can see, as the reaction is going on, we have these bubbles. So in this glass tube, there's actually holes that allow these bubbles to escape, showing you that you have a reaction going forward. We have an acidic solution. An acidic solution containing 1 mole per decimeter cubed of hydrogen ions aqueous. So it is an extremely acidic solution with a pH of 0 actually. And so then we have, so there you have our H+, and we're pumping in H2, so it allows us to therefore create H2 and H+ at the same time. So as we immerse the electrode, the reaction that's taking place is we have 2 H+ aqueous in the solution, and it's going to accept 2 electrons to create H2 gas. And as you can tell, this is an equilibrium because it's a single half cell right now. It's not a voltaic cell. So H+ is going to be reduced, H2 is going to be oxidized. And it all depends on what other voltaic cell we're going to, or half cell we're going to hook this up to determine if we're oxidizing H2 or we're reducing H+. And that's where the those voltage values come from. Again, essentially, we're saying that hydrogen, this hydrogen fuel cell, has a 0.00 volts. That is what we're saying at this point. And based off what's being connected to it, will either be positive or it's going to be negative, depending on which one is going to be the anode and which one's going to be the cathode. So how do we know and understand, or how do we use the standard hydrogen electrode? So the other half cell needs to meet the same standard conditions, and those standard conditions are going to be 1.0 moles per decimeter cubed. The pressure, if the other element is in a gaseous state, needs to be 100 kPa. We need to use a pure substance so that it is not competing with other ions in the solution. The temperature needs to run at 298 Kelvin so that the rates of the reactions and any kind of collisions are at the same rate. The half cell, if it does not include a solid metal, you need to use platinum because it's an inert metal. So what we're going to do is we're going to have our standard hydrogen electrode, and we're going to hook it up to a different standard half cell, zinc, right? Whatever happens to be, silver, copper, magnesium. This is going to complete a voltaic cell. So we have the ability to complete our circuit. The difference that we're going to read in our voltmeter between these two half cells, you're going to get an EMF generated. So electromotive force is going to become generated. And we're going to read it with a voltmeter. And this has become the standard electrode potential, also represented as E theta, for that standard half cell, because we assume that the hydrogen is 0, so any other number is applied to that half cell. And then you can see these in table 24 in your data booklet to see what the numbers are for a variety of different half cells. So let's look at an example and see what I'm talking about through all this process. All right, so we are going to take H2, all right, and we are going to create a half cell, and we're going to hook it up with copper. So when we're hooking up with copper, if you look at table 24, you'll notice that copper has a value, an E theta value, of positive 0.34 volts. So when it's hooked up to hydrogen, since hydrogen's 0, the voltmeter is going to read positive 0.34. That can tell us, therefore, that for this particular reaction, hydrogen was the anode. It was being oxidized. Copper is the cathode. It was being reduced because it is a positive number. A positive number means it's a reduced value. Therefore, electrons were flowing from the hydrogen cell to the copper cell. When you're going through and you're looking at the values in table 24, if it's a positive number, it's going to have a greater tendency to be reduced by hydrogen. If it is a negative value, it has a greater tendency to be oxidized. And hydrogen is going to be reduced. Okay? And so that kind of gives you an idea. So let's look at another example. So if we have zinc, okay, and so we're going to put zinc in. So zinc is in one half cell. It's hooked up to hydrogen in the other half cell. And we're going to get an E theta value of negative 0.76 volts. So it is negative, which means whatever is hooked up to hydrogen is being oxidized. Therefore, zinc is at the anode and it's being oxidized. Hydrogen is at the cathode and it's being reduced. The electrons are flowing from zinc to hydrogen. We can write our complete reaction from this then. So zinc solid reacts with aqueous hydrogen, 2 of them, to make zinc aqueous and hydrogen gas. Okay, and so that just shows you one showing a positive, one showing a negative. So one where hydrogen's being oxidized and another where hydrogen's being reduced. So now we're going to go through and determine how we actually calculate and figure out the standard electrode potential. So some things to understand. The E theta cell, or the standard electrode potential found on table 24 in your data booklet, that number is given for the reduction reaction. All right, so you just need to keep that in mind. And so when we're writing our half cells and writing the reactions that's occurring in the half cell, so for each individual species, we always write it going from oxidized to reduced species to represent the reduction reaction. And that is the value in which is placed into the data table. Now, all the E theta values that you see do not depend on the number of electrons, because it's one electron moving through the voltmeter at a time. So even though zinc discharges 2 electrons per zinc ion, only 1 electron moves through at a time through the voltmeter and resistors and stuff like that. Therefore, we do not take into account the stoichiometric value. So the more positive your E theta cell, the more readily it's going to be reduced. So the anode, or where oxidation is going to occur, is going to be your more negative number, and then you're going to move towards your cathode, which becomes your more positive number, and that's how you know how to set it up. Using your E theta data allows us to make a prediction about where the redox reaction is at, where is it going to flow, direction of flow, and how much voltage is going to be created. Therefore, how do we go through and calculate your E theta? So from your E theta values, we can calculate your EMF for your voltaic cell, and we can deduce the electron flow and the direction of electron flow, and therefore predict the outcome of your redox reaction. The calculation is very simple. So we have our E theta of our cell equals E theta of your reduced cell minus E theta of your oxidized cell. So truly, if you think about it, it is products minus reactants. Just like just about everything we have done is always products minus reactants, because we always write our oxidized cell before your reduced cell, and we always write our oxidized species before our reduced species. Therefore, the calculation is going to be products minus reactants. Remember when you go through and plug in your numbers, the E theta values must be the reduction values. You do not change them for the oxidized species. You just use the number in table 24. Do not change it. And the number is not multiplied by the electron ratio. Just use the number as is. Okay, so if we have zinc 2+, and it's two electrons, because we always write oxidized to reduced, and we look in table 24, and you're going to see that a zinc cell has negative 0.76 volts. Because it's negative, we know it's going to be the oxidized species. We're going to hook this half cell up to a copper half cell. So copper 2+ plus 2 electrons. As you notice, I'm still writing it going from your oxidized to your reduced. Gives us our E theta value. Look in your data booklet, a positive 0.34 volts. Because it is a positive number, that is going to be your reduced half cell. So based on the calculation above, we want to calculate how much voltage we expect in this voltaic cell. So E theta cell equals the E theta for our reduced species for copper minus E theta for our oxidized species zinc. Plug in the numbers, so plus 0.34 volts minus a negative 0.76 volts gives you positive 1.10 volts, just like we saw when we were drawing our voltaic cell earlier. So then it would say, what is your net reaction? And we've done this before, so zinc reacts with copper 2+, creating zinc ions and copper solid, and we expect a voltage, an EMF of positive 1.10 volts. And that's it. That is your calculation. It does not get much more difficult when you're looking at E theta cells. The second kind of calculation we can do is determining the spontaneity of a reaction. So when we do this, you're going to substitute the E theta values into the E theta cell equation based on how it's written and not how it would technically run for a spontaneous reaction. So literally you need to read the problem and write it as you see. So when you go through and you calculate your E cell, if your E theta cell is positive, this is going to be a spontaneous reaction as written. If your E theta cell is negative, this is going to be a non-spontaneous reaction as written. All right, so the example we're going to use is we have a reaction. Our reaction is nickel solid is reacting with a manganese ion to create a nickel ion and manganese solid. All right, so when we're going to go through and do this, in order to figure out our calculation, we need to figure out which one's our oxidized species and which one is our reduced species. So nickel goes from 0 to +2, and manganese goes from +2 to 0. So that means nickel is being oxidized because it's becoming more positive. Manganese is becoming reduced because it's becoming more negative. Sorry. So that means we need to go through and look, and our oxidized species has a value of -0.26. Our reduced species has a value of -1.18. So enter this in. So E theta cell equals your E theta of your manganese ions, because they're being reduced, minus your E theta of your nickel ions, because that is being oxidized. So plug in your numbers, and you're going to get -1.18 minus a -0.26, and you get -0.93 volts. This is a non-spontaneous reaction as written. Therefore, if you hooked this up in a specific direction, it will not run. The third calculation that you need to know is the electrode potential and how it relates to Gibbs free energy. So we're going back to topic 5 yet again. All right. So the calculation in which you need to know is delta G equals -NF E theta, where N is the number of moles of electrons transferred. F, as we noted at the beginning of this lecture, is Faraday's constant. This is known as the Nernst equation. So going through and looking at this, so if we have delta G theta, right? Its units are joules. Negative N, which is moles, times F, which is coulombs per mole, times E theta, which is volts. So you know moles can cancel out. So then if you look at what's left over, you get joules equals coulombs times volts. All right? Now, if you notice, there's a negative sign. And so that negative sign allows us to understand that E theta and delta G have an opposite sign. So that means that if your E theta cell is positive, your delta G for that reaction is going to be negative. And that is why you have a spontaneous reaction. If your E theta cell is negative, your delta G for that reaction is going to be positive. And that shows you why it is a non-spontaneous reaction, as we saw in the previous example. If your E theta cell equals 0, your delta G is going to equal 0, because that means you have run your reaction to completion and it is at equilibrium. So therefore, your voltmeter is an indirect measurement for delta G, as well as the electrode potential. And so you think positive 1.10 volts. You're like, wow, that's such a simple number. But because it's positive, that means it is spontaneous, and it is spontaneous by 1.10 volts, right? And therefore, you can then calculate how much energy is available, and so on, and move on forward. which guess what we're going to do. So let's do an example of how we can use this new calculation. So going back to our trusty zinc, my goodness, reacting with copper gives us our zinc ions and copper solid. As we know, we have an E theta value of positive 1.10 volts. So let's plug in to see what our delta G would be then. Okay, so we know we have -2 because this is the moles of electrons being transferred in this reaction, times 96,500, we round up to 500, coulombs per mole for Faraday's constant, times positive 1.10 volts for the E theta cell that was calculated. Put all this together, we get negative 212,000 joules, and then of course this becomes negative 212 kilojoules. So because it is negative here, positive with your E theta, it is a spontaneous reaction, right? And how much energy is being given off is that value of 212 kilojoules, which then we can go back and relate it back to energetics and all that fun jazz as well. The last calculation or idea in which we're going to look at is comparing relative oxidizing and reducing powers of half cells. If you look at our series here, okay, so we have zinc, we've got copper, right? And then you've got your iodine and you've got chlorine. So we have our metals and nonmetals. So our metals decrease in their E theta values. They become a stronger reducing agent. So the more negative a metal is, the better reducing power it has. The more positive value it is, the more oxidizing power it has. So as nonmetals increase, you can see that like chlorine is more reactive than iodine. It has a higher E theta value. Zinc is more reactive than copper. It has a negative E theta value. All right, so we can have a calculation that we will have KMnO4 reacting with HCl. We want to know, is chlorine gas going to be created? So first thing we're going to do is we're going to write our half reactions. So we've got MnO4 minus reacting with Cl minus. And we want to know, is it capable to create Mn2 plus and Cl2 gas? Is this going to occur? Well, let's figure out who's being oxidized, who's being reduced. So manganese is going to have a positive 7 because oxygen is -2. Chlorine ions -1. Manganese ions positive 2. Chlorine is 0. So manganese goes from +7 to a +2. So it's being reduced. Chlorine ion is going from -1 to 0. So it's being oxidized. All right, so go through and we're going to figure out what are these half reactions so we can pick out the correct E theta value from our data table. So MnO4 negative plus 8 hydrogens plus 5 electrons gives us Mn2 plus 4 waters. So that is the half reaction you want to look for in your table 24. And we see that that has an E theta value of positive 1.51 volts. Then we have half a Cl2 plus an electron gives us a single chlorine ion. That gives us an E theta value of positive 1.36 volts. So now let's go through and see what's going to happen. So E theta cell equals our reduced species, which is MnO4, minus our oxidized species, Cl. So then we plug in our numbers, positive 1.51 minus a positive 1.36, and we are going to get a positive 0.15 volts. This means it is going to be spontaneous reaction. Therefore, we will create CO2 gas. So now we've gone through and we completed and we represented, we have an unknown reaction, and we don't know what product we're going to produce, and we can go through and figure that out, whether or not it's going to be spontaneous in the forward direction. And we could calculate the delta G, because we have our E theta value, we can figure out that how many electrons we need to move through the process, which would be 5, and move on from there. However, something you need to understand is spontaneous does not determine rate. Okay, so that is a big disclosure here. Delta G, as we know, and this has nothing to do with the rate of the cells.